Where were we? Ah, yes. So our goal, we were trying to figure out what a nice function, right? What a nice function is. And the reason we're doing this is because we want to look at the space of all nice functions, and that will be a gigantic canonical space with some action of some adelic group, and that will split up into irreducible representations, and those will be our automorphic representations. But the way we're doing it like this is because it would be no fun if I write down the definition. Somehow that's what I've realized. What we need to do is we need to struggle and work hard and think about the fragmentary examples we have. And try and figure out some unified. I mean, what I've realised that what we're doing is we're kind of pretending we don't know what the answer is, and we're looking at the data we have and we're trying to figure it out. And I would imagine that was how it originally. I mean, that was probably how it originally happened, right? So here's the idea. Of course, in some huge generality, you can have G-connected reductive. I'm just reminding you the question. G-connected reductive. Over K, which means whatever it means. But, for example, G is GLN will work. And we want to define the automorphic forms on G to be the phi from GL. I talked about this last time, right? We've decided, because it worked with GL1, that if we were just looking at functions on all GLN of the Adels, then basically you would have every representation of GLN of the Adels. And you can't have every representation, because that would just mean you could say what was happening everywhere, and that's like on the Galois side, defining a representation by announcing where every Frobenius will go and hoping that such a thing exists, which is extremely unlikely. So we've decided to put some magic quotient here. I mean, this does live discretely in here, so this is not such a bad thing. So currently our definition is this, right? Phi from this to C such that phi is nice. Oh, I'm using them both interchangeably, and I've defined neither of them, so they're exactly the same at this point. One will be naught means Cuss forms.
Oh, sure.
So those are automorphic forms. These phi will be automorphic forms, and the set of all of them is some gigantic vector space A, and the automorphic representations will live in A. And occasionally, you see, the thing is I haven't defined what nice is, right? At some point I'll say, oh, phi, here's an even nicer thing about phi. It could be bounded in this even nicer way, and then suddenly it will be cuspidal. Just like, you know about modular forms? Yeah, see, cusp forms are just modular forms plus more. So that's all. A will contain A0, just like modular forms contain cusp forms. Such that phi is nice. So what do we know about nice? What we know, inspired by GL1, we'd better have, I mean, at the finite places, we kind of know what's going on. Phi has to be locally constant, right? What I'm worried about, let me show you what a function like this looks like. Remember that GL1 of the Adels of K equals K star, well, it's not quite. I mean, GL1 of AK contains K star, the product over all places P of OKP star and K infinity star, right? So there's the diagonally embedded stuff, there's the finite stuff, and there's the infinite stuff. So if we want to define, and this has got finite index. In fact. So to define a function on this, we only really need to define it on this. The index is the class group, right? The class group is the quotient of this by this, because these are ideals and these are principal ideals. So if we want a function on this thing here, we don't have to define it on here. And on K star, it has to be trivial because that's the definition. And on here, it's just a finite amount of noise because we're looking at continuous functions to the complex numbers, and this has a very non-complexy topology. So any function on this to the complex numbers will sort of factor through some finite group. And so all we have left is this, and that's some real manifold, and their phi can actually do something, right? And that's where we were up to last time. Phi, we kind of have rather little, somehow we're a little bit out of control what's going on here. And we probably can't look at all C infinity functions on infinity, because it would just give us too much stuff. So what I'm trying to explain, you see, when we're defining modular, modular forms aren't just random functions on the upper half plane. They have some, like they're holomorphic. We have to try and figure out how to do that. So GL1 of AK is up to a finite amount of noise, so phi is going to be trivial here, right? And this is a finite amount of noise too. Finite in practice. Obviously different phis can have different levels, so the amount of noise can be big. And then here we have some real manifold. So we have to basically define functions on this. But the thing is, we have to make sure they're trivial on this, right? So we end up looking at functions on k infinity star, and the part of this that survives this process here is the elements of k star, which are units everywhere locally. So they're somehow the global units. So we end up with something like that, and we have to look at nice functions on that, right? And this is a real manifold, and this is a discrete subgroup. So this kind of looks like R mod Z or whatever. It looks like products of things like that. So it's not that scary, really. And in fact, for GLN, it's just the same, right? In fact, the same story is true. Maybe I should just. In fact, the same story is true for GLN. I'll prove this. I owe you a proof of this for GL2. So proof for GL2 over Q later. But while we're here, what I just want to convince you is that this, I'm lying. I mean, I'm going to have to write G as GLN, sorry. That should say G of AK. Well, I don't know. I could just do this, right? It's up to you. You can work in whatever generality you like. I don't want to scare people off by going on about connected reductive groups. But, I mean, as far as I'm concerned, they're all GLN anyway. In fact, the same is true for GLN. So what I'm saying is that GLN of the adels of K contains, with finite index, GLN of K times some product over P, GLN of OKP, times GLN of K infinity. We haven't seen a proof of that, but I owe you a proof in the one case that we'll be really specializing in later, which is GL2 over Q. Because for GL2 over Q, I want to really write down some elements of this space. And so it has to be trivial here. And here, this is a finite amount of noise, right? And here's a finite amount of noise. And what we've got left here is GLN of R or GLN of C, things on GLN of R and GLN of C, but they have to be invariant under all of GLN of K, or at least the part of GLN of K that's in here. So you end up with functions on things like GLN of R modulo GLN of Z. That's what this kind of looks like at infinity. And functions from GLN of R to GLN of Z, I mean, you've got to think of a method that somehow, it doesn't sound impossible, right, to write down functions on GLN of R modulo G. It doesn't sound impossible. And even if I start demanding that your functions satisfy differential equations, I mean, it doesn't sound impossible, does it? So writing down functions on this, certainly, like if n is equal to 1, it would be somehow easy, right? Even for general n, if I just, it's not difficult to write down functions on this space. Now, is it difficult to write down functions on this space satisfying all the differential equations I want? Well, I guess we're going to find out. So, GL1. Oh, these blasted differential equations. Right. Okay. Well, let's remind ourselves. Reminder about the case GL1 over Q. Right? At infinity, these are functions, phi is a function of the form on R star modulo Z star. Z star is plus or minus 1, so that's just thought of as the positive reals. And we want examples, right? We definitely want this, whatever this automorphic representation is for GL1 over Q, we definitely want that to contain Grierson characters. I've called them GCs all the way through the course, right? We definitely want that we definitely want that to contain a whole bunch of Grierson characters, because those are going to be my eigenspaces. And for GL1, they kind of gave us the answer, right? For GL1, we saw global Langlands in action. So this nice business, so the conclusion from this is that this map on the positive reals to C star, x goes to x to the s, must be nice. Right? And I showed you in the end of the last lie that actually there's some canonical collection of differential operators in this situation. So r bigger than 0, if that's my Lie group, then my Lie algebra is generated by, so of course G is just isomorphic to the real numbers, so one-dimensional vector space, so it contains some basis vector, let's call it D, right? Which is, D is basically the number one, this curly G is the real numbers, and this D is the number 1. Right? But I'm not thinking of it as a number, I'm thinking it as a differential operator. And I unraveled the definition in the last lecture, and we saw last time that D of f evaluated at x was just x times the derivative of f. So e.g., if f of x equals x to the s, then after a long struggle, I think I convinced myself yesterday that df was s x to the s. Right. And that's s times f, you see. And therefore d minus s times f is 0. Great. So for a Grierson character that looks like x goes to the s at infinity, we found some differential operators that annihilates it. But the thing is, this is supposed to be all the automorphic representations. So we're supposed to be able to see all the Grierson characters, and in particular, what about if we take two different Grierson characters and add them up? That should still be a nice function. After a long struggle yesterday, me and a few other people decided that the product of nice functions might not be nice, because they might not satisfy the right differential. The product of nice functions satisfies the wrong differential equations, it turns out. But the sum of nice functions, definitely we want it to be nice, because I want this to be a vector space. So now we have to do some more calculus, but I prepared it earlier this time, so you won't see me differentiating x to the s live today. So we want sum of Grierson characters needs to be nice. Sum of two Grierson characters needs to be nice. Okay. So therefore, I'm looking at the following map. From r bigger than 0 to c, I'm looking at x goes to x to the power s plus 7 times x to the power t, right? With s and t random complex numbers. I'm scaled one and I've added the other. That had better be nice, right? Is this nice? So there's f of, that's f of x. Well, all I've got is this one differential operator. And if you think about it abstractly, if all the differential operators I'm allowed to have are going to come from this Lie algebra construction, then because this Lie algebra is one-dimensional, that's all the differential operators I'm ever going to get. So I'm stuck with this. And if this doesn't work, we're going to be in trouble, right? So d of f, we know what it is. df of x equals x f dashed of x. So this is now, I think it's s times x to the s plus 7 times t times x to the t. And because s is not equal to t, that is not a multiple of f, yeah? There. So in fact, let's look at d minus s of f. So by definition, that means d of f minus s times f. And so there's d of f. So I'm just going to do, there's d of f and there's f. So s times f, so equals s times x to the s plus 7t x to the t. That's df minus s times x to the s minus 7s times x to the t. So something cancels. The s's cancel. So this is 7 times t minus s times x to the t. So t and s are constants, right? So this is some constant times x to the t. Oh, this is really good, because a constant times x to the t, I can annihilate that with d minus t. Right? D minus t kills x to the t. The thing we had wasn't x to the s or x to the t, but once I apply d minus s, I kill the x to the s part. So therefore, d minus t times d minus s of f is 0, because d minus t kills x to the t, right? It kills x goes to some constant times x to the t. So that's kind of interesting, right? Because now, so just abstractly, we have a huge algebra of differential operators, right? The algebra C of D there acts on the C infinity functions. On the C infinity functions, whatever, from the positive reals to the complexes, right? Remember, this is G of R modulo G of Z or whatever. You know, there's some conceptual. I could just actually, why don't I just think? I mean, it just doesn't matter, does it? G of. This is G of R essentially. So this algebra acts on the C infinity functions, and we've seen the two functions we liked the look of. They somehow were annihilated by a finite index. They were annihilated by an ideal, right? A non-zero ideal. And for the sums of Grierson characters we just looked at, what happened was that there was some idea. I mean, we found there was some non-differential operator. There's some naught not equal to, I don't know, what a differential operator's called. They're only called D. What's another one called that isn't D? D primed. There exists a naught not equal to D primed in C of D, right? D primed was explicitly D minus S, D minus T, such that D primed killed my function there. This sum of Grierson characters was called f. So there was a non-zero differential operator that killed my function, and that non-zero differential operator generates an entire ideal of differential operators, each of which kill my function, right? Because, you know, whatever differential operators are, they're certainly if you feed 0 in, you'll get 0 out, right? These things are linear maps. So once D prime just killed f, if I then take some other random differential operator in here and apply that to 0, I get 0, right? So if I set, if I is the ideal of differential operators, whatever, is D primed, if I is D primed in C of D, such that D primed of f is 0, then I is an ideal, right, of this ring. You know, this is just an abstract polynomial ring. The constants just act by multiplication by constants. D acts by doing that differential operator, and then like D cubed acts by doing the differential operator 3 times, that kind of thing. D minus S means do the differential operator and then multiply S times the number you first thought of. So I is an ideal of C of D, and in the cases we saw, I was cofinite dimensional, right? I had finite codimension. Right, that's the point. That's nice. That's what nice is going to be. You see, so e.g., if I is the ideal generated by D minus S times D minus T, That's some random ideal, right? The product of those two polynomials, ideal generated by them. That's some ideal of C of D, and that ideal has got codimension 2, right? There's a map, there's a ring homomorphism from C of D, surjects onto C squared. I'll just send the polynomial f of D, just goes to the pair f of S, comma f of T. Right? Of course, given two random complex numbers, it's easy to concoct a polynomial that takes one given value at one of them and another given value at the other one. So that's certainly surjective. And what's the kernel is the functions, this is maybe a lousy letter, whatever, H. I'll just call it H because I've tried to use different letters for different things in this course. So F was somehow a Grierson character. So H of D goes to H of S, H of T. The kernel is the polynomials that vanish at S and T. So the kernel is generated by D minus S times D minus T. You see, equals I, which has got codimension 2. Because this modulo I is the image, which is two-dimensional. In particular, it's finite dimensional. So our random thing, x to the s plus 7s to the t, it is annihilated not by D, but by some ideal of finite codimension in all our differential operators. What a kerfuffle, eh? But that's how it works. So I want to talk about ideals of differential operators, but I don't know a darn thing about non-commutative rings. So I'm hoping we can find some commutative rings. And of course, for general G, this is what I talked about at the end of last time, right? General G, we have Lie algebra, we have curly G of the real Lie group in question. You know, this could easily just be GL2 of the reals or GLN of the reals. This is a Lie algebra, so we have kind of a basis kind of E1, E2 up to ED of G. And now, unfortunately, so this was the technical. I'm going to go through the technical bit again. Unfortunately, these elements of this Lie algebra, they act as differential operators on this functions on that real manifold, but they don't commute, right? So EI, comma EJ is some random element of G, right? When you bracket these two differential operators together. And if that random element's non-zero, then these things aren't commuting. So if I start looking at the terrifying non-commutative ring generated by all these differential operators and start asking for some finite index, you know, some finite codimensional ideal, I just don't. I have no control over what's going on. So there's this silly. So now, to proceed, now we have to use this trick of Harish-Chandra, right? So now, let U of G C. So this is just G tends to C, is the non-commutative polynomial ring. Right, C of, I use pointy, I mean, this is not, I don't know what the standard notation is for a non-commutative polynomial. Does anybody know? What do I, like, normal polynomial rings, square brackets. Non-commutative polynomial ring?
I've seen angle brackets.
These? Yeah. You see, because I sometimes do p-adic geometry, and then I see these meaning something else. Let's go with angle brackets then, thanks. E1, E2, up to ED, right? So the idea is that EI is supposed to correspond to little ei. So this is, you know, it's exactly doing the job we want. E1 times E2 is not E2 times E1 in this ring, because it's not a polynomial ring. I have to keep track of the orders. But I can mod out by the bi-ideal generated by whatever, EI, comma EJ equals whatever it is. You know, if this, if EI, comma EJ is the sum of AIJK EK, right? But if you think about it, these AIJKs determine the Lie algebra completely. These AIJKs are random, real or complex numbers. I guess real numbers in this case. And if you know all the AIJK, you know the Lie algebra. But the problem is how you're going to check the Jacobi identity. We don't need to worry about that. I'm just going to define EI, EJ, take away the sum of AIJK, EK. Right, I'm just going to look at the ideal generated by all of those things, and now I've got this random algebra, something with a ring structure, and it still seems to have some copy of the Lie algebra in it, because it's got all these e's that are somehow corresponding to the little e's, but now these are elements of a ring, and I can multiply them together. And I can multiply them together and get like e2 to the power 100. That's a perfectly good differential operator in here. Now the problem with this ring is it's non-commutative, and I've quoted out by the relations I want, but it's still non-commutative. But Harish-Chandra tells us what the centre is. So we need to, I'm telling you the general story, but of course for GL2 over Q, we're going to have to unravel all this at some point. So that's coming later. So just bear with me while we do the general thing. So Harish-Chandra the centre of this universal enveloping algebra is a polynomial ring. Turns out to be C of T1, T2, TD, W, where T1 up to where D is the dimension of a maximal torus. Dimension. I'm in trouble. I don't even know if it's the maximal torus or the maximal split torus. Curses. Let's not worry. This might be wrong. This might be the maximal. Let me just do. Let's forget. For general G, I don't quite understand the details. Let's do G as GLN, right? Let's just do G as GLN over Q for a minute, because then I understand the details. Then the Lie algebra here is some matrix algebra over the reals. The complexified Lie algebra is a matrix algebra over the complexes. So there's n squared of these little e's, and the theorem of Harish-Chandra says that the centre of the universal enveloping algebra in this case is a polynomial ring in n variables this time, fixed by some W, and W is the symmetric group Sn, the symmetric group on n elements. And how does it act on this polynomial ring with T? It swaps them round, right? Permuting the Ti's. There. So Harish-Chandra gives you some theorem that explicitly works out for you this centre of this universal enveloping algebra. So whatever. And the proof isn't so hard, but I don't want to talk about the proof. I want to talk about two explicit things, right? What have I done?
The relations for the universal.
Have I got it wrong? Oh yeah. Oh yeah, I see. That's my definition. Yeah, it would be much better to write it the way you wrote, the way you're suggesting. There. Thank you, Jackie. There. So, of course, I could define box EIEJ. Actually, that would be a really bad idea. This is a really good idea. Thank you even more. Now I understand what you mean. Yeah, that's the correct answer. That's the correct thing to write. Yeah, so Harish-Chandra says, bar all this kerfuffle, we get some random non-commutative ring, and inside it, we can isolate some random commutative ring, and a machine tells us what this random commutative ring looks like. Okay, that's what Harish-Chandra's theorem says. And as an upshot, this is a canonical source of possibly higher order. See, everything in the Lie algebra is all like d by dx or x d by dx. There's stuff in here, but just like d2 by dx squared plus d2 by dy squared, right? A canonical source of higher order differential operators. Okay? And you just got to live with it. You've got to live with it. Because you know, people can tell you that modular forms are an example of automorphic forms till you're blue in the face, but at the end of the day, modular forms are holomorphic functions, right? And why are holomorphic functions so interesting in this context? Especially when I've got functions on GL2 of the reals. What's that got to do with holomorphic functions? GL2 of the reals isn't even a complex manifold. So someone's got to really explain to you the calculus at some point. And it took me years. I knew nothing about this until I was like a tenured faculty. It was just something that everyone was like, yeah, differential operators. So anyway, here's how it works. So as I say, this is a canonical source of higher order differential operators. It's just the differential operators that commute with all the other differential operators. Right? That's how you can think of it. This universal enveloping algebra is clearly generated by these random first order differential operators coming from the Lie algebra. And so basically we're writing down random differential operators that commute with all the obvious differential operators. That's what we're doing. It also, there's another way of thinking about it. These turn out to be the bi. These are also the bi, if you understand what this means, the bi-G invariant differential operators. These are differential operators which commute. The group acts on itself, right, on the left and on the right. And these differential operators turn out to commute with both the left and the right actions. The universal differential operators are all left invariant, and these ones are the bi-invariant ones. So that's chatting about what's happening here, various ways of thinking about this canonical collection of differential operators. Now we want to talk about what's happening here. And what's happening here is that this is the universal enveloping algebra of a Cartan subalgebra, which in my case is a fancy way of saying, so these T's, what are these TI's? There's some torus T, right, which is star, star, star. What example am I doing? I'm doing GLN over Q, right? This lives in GLN. Okay, so there's my torus, and T of R. That's a Lie subalgebra of G of R, which is GLN of R. And sorry, that's a Lie subgroup, and that Lie subgroup has a Lie subalgebra. And I think it's called H. I don't quite know. Isn't it called H? What is that? What's going on with that? Why isn't it called T? Can I call it T? That would be a really bad, that would break with tradition. This H looks like the upper half plane. I'm going to call it T. Does T mean something else? When you see T, that looks like a really good name for the Lie algebra of T. I'm going to call it T, right?
The algebra of upper triangular matrices.
That's B, yeah?
I mean, I've never seen math practically.
You have now. Let's call it T. Hang the H. I'm sick of writing H and trying to make it look different to the upper half plane. There's going to be upper half planes later. I've got to get on to modular forms. This is like the last lecture. T of R is the Lie subgroup of G of R. So there you go. T lives in G. There's the Lie subalgebra. I'm sorry, every mathematician. I'm just going to call it T because it's a sensible name. I don't know how it ended up being H. It's H for Cartan, right?
In the representation theory, that's also. Like H is that.
Because H is 0, 1, negative 1, 0 or something. Or what? No, 1, 0, 0, negative 1. Yeah. I don't know who we have to blame for that. Who would call a circle H? Does anyone know any foreign words for circle? Do any of them begin with H? Not any that I can think of. Anyway, forget it. It's going to be called T for this lecture. Like, what a daft idea. T is the Lie subalgebra, and that T is now, I mean, of course, what's the T is just isomorphic, right? This is how many, there's n stars. This is isomorphic to GL1 to the power n, right? It's not a mystery what T is. It's GL1 of R to the power n. So it's an n-dimensional thing. So this Lie algebra will be n-dimensional, right? T has basis T1 up to Tn. Okay, and so the universal enveloping algebra of T is C of T1 up to Tn. And there's no relation, so I can't get it wrong this time. Because this is a commuting Lie group, so these Lie algebra elements commute. So what's really happening is you've got some function on G, you restrict to a Borel, you average down, you get some function on some torus, there's just some story. Okay? And then W is the Wahl group. And then so W is just the normalizer ng of T modulo T, you see. So it's Sn, because it's the permutation matrices. Permutation matrices are from a group, from a vector space point of view, they're linear maps that permute the basis elements around. So they permute the basis elements around. So what do they do to T? They just kind of permute the order of the little stars. So lo and behold, they permute these T's, and that's how it works. In fact, and as I mentioned, we can work this out in this case. It turns out it's still a polynomial ring. It's a theorem of Isaac Newton, apparently. You didn't know he was involved, did you? So there you go. I'm not sure if he's still active, but somehow, obviously, in the 60s. So anyway, so this is so U of G is C of T1 up to Tn W, which is C of, I mentioned this last time, right? Sigma 1 up to sigma n. There, where sigma, sigma I is the ith symmetric polynomial. What's it called? The ith Newton polynomial or something? Yeah. By a theorem ascribed to Newton. Now, I've got to actually finish today, so I can't just waffle. I should actually look at what my notes say. Blah, blah, blah. Done all that. So the problem, how do I prepare these lectures? I go away and think about the things I want to say, and then somehow for each of those things, I kind of think really hard to see if I understand them, and to try and remember how I struggled when I was learning them. Then I write them all down on a piece of paper. Then I come and give the lecture, and I never even look at the piece of paper. I just somehow remember the things I was struggling with. Oh. Apparently we're on to GL2. Am I really not going to give you the definition? No. Oh, yes, coming. 2 pages time, apparently, unless I wander. Right. Let's do an example. There's a fun exercise in here that I'll leave it to you. It's good fun. Huh? What have I done? Hello?
Can I clarify on the top board over there?
Please do. Oh, that's wrong, yeah? It's the centre, yeah? I have no idea what U of G is. I mean, there are people that do, but I ain't one of them. Thank you. The centre is something I understand. So, what do we know? Example for GL2 over Q. All this machine, the Harish-Chandra machine, the Harish-Chandra-Newton machine, says that the centre of the universal enveloping algebra of G is going to be a polynomial ring in 2 variables, right? Because n is now 2. C of 2. I need names for these 2 variables. Why don't I call them triangle and Z? There. So these things here are 2 differential operators, right? 2 differential operators. And these 2 differential operators must be kind of magic differential operators that commute with every other differential operator. And we know there's 2 of them, and we don't really know much else about them. I guess one thing's worth remarking here is that sigma 1 of sigma. If I have these T's, I've got T1 and T2, and then sigma 1 is T1 plus T2, and sigma 2 is T1 times T2. That's how Newton's theorem works in this case. And that one looks like it's kind of a first order differential operator, and that one looks like it's a second order differential operator. And so maybe one of these is a first order differential operator, and maybe the other one's a second order differential operator. So let's see if we can spot them. And once in my life I did this calculation, and it took ages, and I wrote it up as a note and put it on my website. And I'm not going to do it now, but I'll tell you what the answer is. So I'm going to write down some differential operators that commute with everything. So watch this. So G is the Lie algebra, right? It's the Lie algebra of GL2 of R. Okay? And so that's really 2 by 2 matrices over R. But we have to be a little bit careful. It's 2 by 2 matrices over R. What structure do we have here? Well, it's a real vector space, that's fine. And it has a Lie bracket on it, that's fine. But it does have a multiplication on it, but we need to forget that, right? Remember, forget the multiplication. Forget the multiplication. We only have the bracket, really. Okay, that's what we have. And it turns out that bracket xy is xy times yx, but that's just some coincidental calculation, right? You've now got to forget that this has a ring structure, because we're going to take some we're going to force a ring structure on it by taking some universe enveloping algebra, and that will somehow be a different ring structure. So there's my Lie algebra, and this has a basis, 2 by 2 matrices, and it's a very famous basis, and all the elements have got famous names. So standard basis for G. Standard basis for G. It's called E, which is 0, 1, 0, 0, and F, which is 0, 0, 1, 0, and H, which is 1, 0, 0, minus 1, and which we now think is the source of all our problems, and Z, which is 1, 0, 0, 1. It's interesting, isn't it? I've called it Z, but it's somehow, I don't know, it commutes. You wonder whether that Z's got anything to do with this one, don't you? So there is our Lie algebra. And now, of course, we can start doing the boxing stuff, right? The boxes. We could do boxes. We could do, and apparently, I worked these out last night, but apparently E, comma F is H. So I'm saying E times F minus F times E is H. And you can do the other things as well. E, comma H is minus 2E. And F, comma H is 2F. And kind of anything, comma Z is 0. Z commutes with everything. So there's examples of my Lie algebra structure. So remember, I've forgotten the ring structure on 2 by 2 matrices. I've only got this Lie algebra. I've got this 4-dimensional vector space with some silly bilinear bracket on it. And I want a ring, and I've forgotten the fact that I had a ring already. So let's take some universal enveloping algebra, right? U of G, let's complexify while we're here, is now some non-commutative polynomial ring with 4 generators. And I really want to distinguish the generators from those matrices, right? E, F, H, and Z. Okay, modulo some relations. Now, see if I get it right this time. Modulo relations, and the relations are things like E times F minus F times E is minus H, etc. You see, that then corresponds to this one here. And now this is the one point where you just have to be careful. If you pretend, you mustn't think of these as matrices now, right? That's why I've changed the notation and everything. This is not anything to do with the matrix that you get when you multiply E by F. This is just some abstract setting where E, F, H, and Z are abstract operators. And I'm quoting out by that ideal. So I know the center of that ring is generated by 2 operators. And if you ever do one calculation in your life involving non-commuting differential operators, then why don't you make it this one? It's a sort of nice, fun exercise. Is that if I define triangle to be 8 squared plus 2 times EF, this is a number 2, plus 2 times FE. So that is an element of this ring here, right? And as I say, I really want to stress, h squared is nothing to do with the matrix little h squared, right? H is an abstract variable in this ring. H squared is another abstract variable in this ring. So there's a random second order differential operator. Then why don't you check that this thing here commutes with E, F, H, and Z. Because it's the one time I ever felt I understood analysis was when I did this calculation. And it's just algebra, really. So you've got to, it's like it's really scary because it's a non-commutative ring, right? So you multiply on the right by E, you can't rearrange, right? You get FEE, and you want to make sure that it's kind of EFE. So you're going to have to somehow figure out how to get FEE into EFE. So you need to kind of commute E and F. So you need to use relationships like this, and then you get some H, and it's like, you know, it gets a bit muddly, and then you realise what a nightmare it must be working in non-commutative ring theory. So, I don't know. That's an exercise that I thought was worth doing. So there it is, right? I pulled it out of the hat. There is actually a rather canonical, there's a clever way of doing it that doesn't involve pulling anything out of a hat. You can look at the killing form on SL2R, and that gives you some identification of G with its dual. And we choose a basis, e.g. EFH, for the Lie algebra of SL2R. And then we look at the corresponding dual basis and take the dot product. And that's such a canonical thing, if you understand what those words, you know, what these things like killing forms are. That's such a canonical construction that it's going to be well-defined and independent of all choices and some magic canonical element. And you do it in this case and you get that, up to about a factor of 4 or something. There are factors of 4 kicking around that will be suppressed constantly. So there you go. So I guess the other thing that's kind of obvious is that little z commutes with everything. So capital Z commutes with everything here. Like there's relations of the form EZ minus ZE equals 0, right? So clearly, delta and Z are certainly in this center of this universal embellishment there. Okay, and it turns out that that's it, right? That's what we want. That's the, you know, that these generate the. It turns out these generate the center. The center really is C of delta, comma Z. So there's our differential operators. Z is an extremely uninteresting differential operator because it is controlling what the center is doing. Right? So somehow saying that Z of F is SF just kind of says that on the center you look like X goes to X to the S, which is somehow what we saw for GL1. But this other differential operator that's somehow fallen out of the sky must be some kind of differential operator that must be relevant to the theory of automorphic forms, and so we should kind of try and figure out what it is. And I think I did at some point. Yeah, I did. So how can we understand delta? I mean, delta, what is this delta? Delta is some second order differential operator on functions on the upper half plane. Sorry, I mean, that's where we're going, the upper half plane. Functions on GL2 of R. Right? And in fact, it only operates near the I mean, I may as well put plus here, because it's only acting, these things are differential operators kind of acting near the identity. Well, yeah, let me put plus. It doesn't matter. I'm just taking a component. Right? GL2R has got 2 components, the stuff with positive determinant and negative determinant. So it's certainly a second order differential operator on these things here. But this is kind of, I don't know, let's cut things down a bit. Let me remind you, here's a reminder. So this group GL2 plus of R, which is the matrices of the form A, B, C, D, such that AD minus BC is positive. That group there, that's a group, and it acts on the upper half plane, right? And that's the proper H That's a half plane H. Via the usual formula, right? Tau, A, B, C, D, tau is A tau plus B over C tau plus D. So GL2 of R acts, and it acts transitively, right? What I'm trying to argue is that I should be able to get a function on GL2 plus R if I have a function on the upper half plane. You see? So there's a map, there's a surjection GL2 plus R onto the upper half plane. Just a surjection of sets, right? Well, a surjection of real manifolds, I guess. I'll just say gamma to gamma of I, right, is AI plus B over CI plus D. So if I give a function on the upper half plane, then I get a function on GL2 plus R. And we could attempt to apply that differential operator and see what the differential operator does. So I should perhaps be a little bit more explicit about what just happened here. We had a group acting on a set, and I gave a surjection from the group to the set by just choosing a random element of the set and letting the group act on it. So in fact, this would identify the set with some quotient of the group by the stabilizer, right? So the stabilizer of it's somehow worth remarking at some point that gamma in GL2 plus R, such that gamma of I is equal to I. What is that? That's kind of R star SO2R. So this is the center of GL2 plus R. This is the scalar, not just the diagonal matrices, the scalar matrices living in GL2 plus R. And for those of you that can't remember their special orthogonal groups, this is the circle. Cos theta minus sine theta, cos theta. That's what SO2R turns out to be. And so what we're really saying is that the upper half plane is this group acts on the left, so I'm saying that it's GL2 plus R over R star SO2R. Right. What have I done?
I mean, the center of the stable. Is the R positive or R?
I think I'm okay. I think if lambda is negative, then lambda 0, 0, lambda is positive. So the center's not connected. How weird is that? Is that something's wrong? If this is connected, how can the center not be connected? Have I done something wrong?
Well, like the negative trace elements aren't in the group that you're working with. Right, they're in GL2, but they're not in GL2 plus.
GL2 plus means det positive, right? GL2 plus means det positive. So it contains negative the identity, right? Yeah. Isn't life wonderful? Right, so there we go. So now let's say I've got some function. So now say I actually have some function f is on the upper half plane to the complexes. That might look familiar to some people. So we've got some function on the upper half plane, and we let f be the associated function on GL2 plus R. So now we've got a function on GL2 plus R. So now we can apply our fancy differential operator. So then delta f, that's now also a function on GL2 plus R. But because everything is kind of invariant, f was invariant under that subspace there. And this commutes with everything. So this is also invariant under that subspace there. So this thing here will descends to a function, whatever, we could just call it triangle f, right, on the upper half plane. So what I've done is I said that some hugely general machine that spits out canonical differential operators, if I apply it in this case, I end up with some random differential operator on functions on the upper half plane. And I attempted to work out what this operator was. And if I've got it right, I think that up to a constant, the reason I'm worried about constants is that different sources normalize. Do you see? This triangle is just some polynomial generator. I can scale it by some non-zero real or complex number, and I still get a triangle. And different people use different normalizations for the triangle. So up to a constant that I'm a bit hazy about, delta of f is just what? I wrote it down somewhere. I could have sworn I worked it out. Oh, here we are. Minus y squared d2 by dx squared plus d2 by dy squared. So forms that are annihilated by that triangle operator, I guess y is the imaginary part, right? So z is in the upper half plane. Z is x plus iy, of course. That's my notation. Because the upper half plane, y is never 0. So if delta of f is 0, it means that f was annihilated by these things here. And you see every holomorphic function is annihilated by that operator. That's somehow the Cauchy-Riemann equations. As is every kind of anti-holomorphic function, as is a whole bunch of other things, right? A whole bunch of other random holomorphic, random harmonic functions that aren't holomorphic or not. And furthermore, when we were doing that d in the GL1 case, I didn't demand that d of f was 0. I just demanded that d of f was lambda f, where lambda was s. So maybe we're interested in functions such that delta of f is kind of some random number times f, where that random number might not be 0. See, maybe those are nice as well. And they are nice. And that's why the theory of automorphic forms of GL2 of Q isn't just the theory of modular forms. That's why you see non-holomorphic things as well. So you see what we want. Remember for GL1 over Q, our definition of nice was that there existed some I living in C of D, finite codimension, such that such that delta of f is 0 for all delta in I. Okay, and so here it looks to me. So here, our universal, whatever it is, our centre of our universal differential thingy, what's it? Is polynomial rings in 2 variables, is this, there. And so I want some finite codimensional ideal that's annihilating this. And so, I mean, ideally, these 2 things could just act as I mean, that would work, right? If these things acted as scalars, that would work.
Sorry, I can't read this. What's the lowercase delta?
A random element of capital I.
Oh, that's
I've run out of, because I don't really work in the field, I don't know what good letters are for differential operators. And I've used capital D and I've used delta, and that's my source has run out. So do you know any more? I mean, what's a good letter? What? Aleph? Yeah, that's a great idea. Aleph, that's for all Alephs in I. Right, so all differential operators are now going to be called by Hebrew letters. That's a fabulous breakthrough in the area. So what have we so the upshot here, it looks like we're interested in differential in functions on the upper half plane to the complexes, so this is called f, such that kind of triangle times f is some constant times f, right? Lambda some constant, okay? And then z has to act in some certain way, but then z is just some, and then somehow zf and zf is going to be mu times f, right? So this will be something with some central character. Right, this won't be some interesting thing. I'm just saying how the centre acts, and the centre will act by scalars, and this will somehow be the scalar that we're going to be read off. But this is somehow the equation that's coming out here. If we want,
You
what have I done? Z mu, Z of f, thank you. ZF is mu times f. So that's some uninteresting equation that's so uninteresting I wrote it down wrong. And that's some equation that I'm attempting to argue is somehow motivated by, vague ideas of what we know. And those of you that know about modular forms, those are holomorphic functions, so they will indeed satisfy that equation with lambda is 0. And those of you that have read about mass forms, which are other examples of automorphic representation, somehow these mass forms satisfy this with lambda non-zero. Right, are we ready to give the definition? Maybe I should say, not quite. Recall this theorem of Deligne. Let me just explain to you how these non-holomorphic forms might fit into the picture. Recall this theorem of Deligne. If I've got f some modular form, Deligne and others, right? Deligne et al. F some modular form which is an eigenform for the Hecker operators. There's some compatible sequence of some compatible system of Galois representations, Gal q bar over q, to GL2 of q lambda of QL bar, right? So this is some famous theorem of Deligne, and one of the things that rho f satisfies is that the determinant of rho f of complex conjugation is always -1. So the easiest case for this very technical, difficult story is when f is somehow weight 2 and trivial character, and then Eichler and Shimura attach an abelian variety to f, and the Galois representations are just the Tate module of the abelian variety as L varies. So in the simplest case, f has got coefficients in z, and the abelian variety is the elliptic curve attached to f. And then these are the Tate modules of the elliptic curve. And the reason that this determinant's -1 is because of the Weil pairing. The Weil pairing is some alternating pairing that puts some kind of, story on what's happening. And it forces the determinant to be the cyclotomic character. And the cyclotomic character sends complex conjugation to -1 because it maps every root of unity to its inverse. So there's a story behind that, but at the end of the day, det of rho for complex conjugation is -1. But the thing is, I can think of loads of compatible systems of Galois representations that don't have this property. Okay? So now let just let f of x be some random irreducible cubic polynomial, right? Irreducible over q with 3 real roots. Okay? So, and then let's just let k be the split, 3 real roots alpha, beta, gamma. Right? And then we just let k be the splitting field of this thing here, q of alpha, beta, gamma. And the chances are, if the discriminant of this is some square, then rotten luck, but the chance of that happening is 0. So the chances are that gal k over q is isomorphic to S3. Right? Splitting field of a random cubic. The chances are that these numbers will be sufficiently independent that given any permutation of them, I can beef that up to a field automorphism of k. So that Galois group's S3. But the thing is, I demanded that all the roots were real, so complex conjugation in here is trivial. It's a trivial element. So S3's got a 2-dimensional representation, right? So let me fix rho 0. Rho 0 from gal q bar over q. That's going to surject to gal k over q. And that's isomorphic to S3. And there's some standard 2-dimensional representation. And it's going to go to GL2 of C. But it even goes to GL2 of Q, doesn't it? I can realise it over Q, I think. I'm going to look at Rebecca. She lectured this course. It descends to Q, right? It's Q, S3 acts on Q cubed. And I'm going to go with that. So there we go. There's some standard irreducible 2-dimensional representation. And det of rho 0 of complex conjugation is det of row 0 of complex conjugation is det of row 0 of 1, which is 1, right? Because complex conjugation, I've fudged it so that complex conjugation, acts trivially. So I've got a compatible sequence of L-adic Gower representations here that somehow aren't covered by Deline's theorem at all, right? No way is Deline predicting the existence of such a thing. Okay? So there we go, given row 0, and now for all primes L, and I get row L from gal cube R over Q. Here's a compatible system of L-adic Gower representations. You know, I'm just going to go via, that's row 0, that goes to GL2 of Q, and then that just goes to GL2 of QL. Right? There's two kinds of compatible systems of L-adic Gower representations. There's stupid ones like this, and then there's genuinely complicated ones where each element in the family, you know, you take the element in the family at L, and it's probably infinitely ramified and vastly complicated at L. That's normally what happens. And then as L varies, you get a whole bunch of genuinely different representations, like all the different cyclotomic characters. But this is a bogus case. But I get a compatible system just by one finite image representation. So what the heck, right? If you believe Langlands reciprocity conjectures, or Clozel's variant of them or whatever, then attached to that system, there should be some, these row L's should be attached to some automorphic representation pi, right? To some pi. Okay, and modular forms don't cut it. And this is what Hans Maas did, right? He solved this problem by simply writing down a function on the upper half plane that kind of gave rise to this row L, right? He just wrote down a harmonic function. Well, he wrote down a function from the upper half plane to the complexes that was not holomorphic. It was invariant under some gamma 1 of n, where n is the conductor. N is the conductor of row 0, and somehow everyone realised that he'd done something. He'd done something, but somehow this triangle of f was just lambda of f, and lambda wasn't 0. So this is when you kind of realise that not only do we have to move on from holomorphic forms, but also, you know, maybe as long as they're eigenvalues for this Laplacian, maybe we're in good shape. Are we actually going to do it? Yeah. What's the time? Oh, curses. We could break it. No, let's write down the definition. Right. Definition then. So let me just do notation first. Let's have G, connected reductive group. Over a global field. Well, over a number field. Okay. Well, the definition depends on some choice of a maximal compact subgroup. So let me fix, not everyone calls this K infinity, but throughout this course I've used K infinity to mean something else. I don't want to change now. So I'm going to call it H infinity. This is a thing that a lot of people would call K infinity, equals a thing that many people would call, that many people would call K infinity, because compact at infinity is a maximal compact subgroup of the thing that I want to call of G of what I want to call K infinity, which is the product of KV, V infinite. So of course the example you want to keep in your head is e.g. G is GLN over Q, then G of K infinity is GLN of R, and I need to come up with a maximal compact subgroup of this guy, and so H infinity is going to be ON of R. Orthogonal matrices. So there we go. That's an example of what H infinity looks like. So we saw, you know, when we did GL2 plus, we saw H infinity plus, which was SO2R, showing up earlier. Right. So some function phi, a function phi from G of K over G of the Adels of K to C is called an automorphic form. So that's what this course is going to be about, automorphic forms. If. It's nearly time to stop, right? Let's write down the definition. And, you know, really, what I could give it you as an exercise, actually. I think we've said enough. I could give it you as an exercise. I've given you so many clues that hopefully this definition will not be scary. So it's called an automorphic form if firstly what? There's some continuity, right? Phi is smooth, right? So as I say, I got a rather nice question some time ago. Thank you for your questions, by the way. Some people have asked me really good questions. Somebody asked me if this had the structure of a manifold, and I was reluctant to put the structure of a manifold on it. But I still want to talk about smooth functions. So phi is smooth. What does that mean? i.e., if we write G of the Adels of K is G of the finite Adels of K cross G of the stuff at infinity, right? And this contains some x, y, with x here and y here. If we write G of AK like that, then I can regard G as a function of two variables, x and y. Then for fixed x, this is just a function of y, and y is in this random Lie group, which is like GLN of the reals. So for fixed x, phi is C infinity with respect to y. So infinitely differentiable. And for fixed y, I can now regard phi as a function on this set here, which is locally pro-finite, and I'm just going to demand it's locally constant. Phi is locally constant. So there's my smoothness condition. So secondly, do you remember we talked about functions on GL2 of R, but the examples, like pretty much all the examples that I've hinted at or that we know about come from functions on the upper half plane. So they're actually functions on GLN of R modulo H infinity somehow.
The mass ones wrote down that they are in fact C infinity, right?
The mass forms, they're C infinity, yeah. They're just not complex differentiable. In fact, why the heck are we interested in complex differentiable functions? Because this upper half plane isn't a complex manifold, right? But like the upper half plane is GL2 plus R, the following real manifold, modulo R star SO2R. I mean, why the heck, that's not a complex manifold. So why the heck would we be interested in holomorphic functions? It's just like... Deline wrote down the axioms for a Shimura variety. So if G, here's how you prove the global Langlands conjectures. Take G connected reductive group over a number field, and then assume that G satisfies Deline's axioms for a Shimura variety, which means in particular that things like this have got a complex structure. And then you build the Shimura variety, you find some model over a number field, you take the cohomology, and you find the representations in that. That's somehow a summary of the vast majority of work that's been done on Langlands reciprocity conjecture. The problem with Deligne's axioms is they're not even true for GL3. If you change all those 2s to 3s, then you get a real 5-dimensional manifold. So it definitely doesn't have a complex structure. So I want some kind of finiteness. You see, I've already got some kind of finiteness at the finite places. I've got locally constant, but I need even more, so we'll get more in a minute. And I want some kind of finiteness under the action of H infinity. So let me write down what this means. So this is kind of well behaved on this, phi is well behaved on compact subgroups. This is some kind of something that's related to admissibility somehow. So what do we say here? I.e., there's two conditions, right? There's compact subgroups at finite distance and compact subgroups at infinity. So this is two parts. 2a, there exists some UF living in G of the adels of F, the finite adels of F, there, compact open, such that phi of G times U equals phi of G for all U in UF. I put UF because it's the finite part. That's the finite part. And at the infinite part, you see, the infinite part is slightly more delicate. Let me just pretend that G is GLN, or even GL2. Then this UF could be like GL2 of Z hat, but it could be a smaller thing. It could be a finite index, it could be the analog of gamma 0n. It could be the things in GL2 Z hat which are congruent to star, star 0, star mod n. And then if you demand that phi is constant on that huge finite index subgroup of GL2 Z hat, then if you actually let all of GL2 Z hat act, then phi might move around a little bit, but it would only span a finite dimensional vector space. So I'm going to say the analog of, so at infinity, I'm going to let the whole, the problem is, you see, these compact subgroups are totally different. These compact subgroups, this H infinity, things like that, that doesn't have finite index subgroups. It's of a very different nature. So I have to kind of reformulate 2a in some kind of space spanned by something its finite dimensional way, and then you'll see it was some analog of what I'm going to write down now here, which is 2b. So I want to look at the complex vector space spanned by the functions x well, I'll call it g goes to phi of g h infinity. As h infinity moves, is finite dimensional. As h infinity runs through all of h infinity. Okay, so at infinity, so here's an example, e.g., phi could be trivial, right? On h infinity, right? Like modular forms. Like some functions from the upper half plane to the complexes. Right, if you've got a function on the upper half plane, then I showed you how to regard it as a function on GL2 plus R, and I just said, oh, just let it be trivial on O2 of R. So phi could be trivial, and then this function is just phi again, but what I'm allowing is that maybe there could be some finite dimensional representations of this showing up. We'll see an example of h infinity acting non-trivially if I ever get to it, which I will. So there's 2, and now all that work, like the last hour and a half, was to do 3. This is the thing that I found most incomprehensible. Right, I'm going to write down the automorphic form attached to a modular form next. Well, we're going to have a break. But then after that, I'm going to write down the automorphic form attached to a modular form. And you'll see this happening. You'll see h infinity acting slightly differently. So you'll kind of have a good feeling for the definition. But somehow, I never quite understood what was happening with 3. So, I don't know. Maybe you'll do better than me. So there exists some ideal I living in the center of the universally enveloping algebra of the complexified Lie algebra of G. So G is the Lie algebra of G of K infinity. So is this some ideal here, a finite codimension, such that for all differential operators Aleph in I, Aleph of phi is 0. Right? By which I mean what's going on at infinity. Aleph of the function x in G infinity goes to phi, I'd call it y. Y goes to phi of x comma y is 0. Okay, so this is for all this thing here and for all x in G of the finite adels. So this just says that whatever's happening to phi at infinity, it's being annihilated by a huge number of canonically defined differential operators. And there's one more part to the definition, but it's really boring. So part 4, some boundedness, some growth conditions. Boring growth conditions. There, kind of phi of x comma y is at most some constant times the norm of y to the power n. Right? That's all it is. Where this is some sensible norm. Some sensible norm on GK infinity. Just take any norm. I mean, make it sensible. It's fine. I don't want to say any more about growth conditions. What was I doing? Was I defined? Oh, I've rubbed off. Oh well. So I think that board used to say phi is an automorphic form if blah blah blah. We filled the entire. You see why it took me so long? It doesn't even fit on the. Anyway, that's the definition. That's a good place to stop, right? There's the definition, and then I'll give one more lecture, and maybe I'll tell you what an automorphic representation is. I'll see you in 15.